Welcome to Structural Patterns. In this video, we are looking at the Flyweight pattern, a technique for keeping memory usage under control when your program needs to create enormous numbers of objects that are mostly identical. By the end, you will know exactly when to reach for it and how to implement it yourself. Imagine a text editor that opens a novel, a million characters on screen. If you create one object per character, and each object stores its font family, font size, color, and screen position, you are duplicating font and color data a million times over. That redundancy is pure waste. The same problem appears in particle systems, tile-based maps, and anywhere you instantiate huge numbers of nearly identical objects. Think of old-fashioned movable type printing. The printer has one metal block shaped like the letter A, and reuses that same block everywhere the letter A appears on the page. The shape of the letter is shared. The position on the page is supplied at print time. Flyweight works exactly the same way. One shared object, many usage contexts. The key insight is separating two kinds of state. Intrinsic state is everything that is the same, no matter where the object is used. For a text glyph, that is the character code, font, and color. Extrinsic state is context dependent, the row and column where this glyph appears. A Flyweight object holds only intrinsic state and is shared. The caller passes extrinsic state in at the moment of use. A FlyweightFactory caches these shared objects, so each unique intrinsic combination is created only once. Let us walk through this top to bottom. First, the glyph context interface carries row and call, that is the extrinsic state the caller owns. Next, the glyph class is the Flyweight. Its constructor takes char, font, and color, the intrinsic state, and those fields are read-only, meaning they never change after construction. The render method accepts a glyph context and uses both the stored intrinsic fields and the passed-in position to do its work. Then glyphFactory keeps a map called cache. Its getGlyph method builds a string key from all three intrinsic values, checks whether that key already exists, creates a new glyph only if it does not, and always returns the cached instance. Finally, the client splits the word hello into characters. The letter L appears twice, but getGlyph returns the same glyph object both times, so 5 characters produce only 4 unique instances. At runtime, the flow is always the same. The client asks the factory for a Flyweight, the factory checks its cache, and either returns an existing object, or builds a fresh one. Because every caller sharing the same intrinsic values gets the exact same object reference, you might go from a million object allocations down to a few hundred. The cost is that extrinsic state has to live somewhere, usually in the client or in a parallel data structure, and be passed in every time you call a Flyweight method. Flyweight pays for itself only under specific conditions. If you are genuinely allocating millions of objects and profiling shows memory is the bottleneck, and most of those objects share a lot of state, then splitting intrinsic from extrinsic state is a clear win. But if your object counts are modest, or each object is largely unique, the pattern adds architectural complexity with no measurable benefit. Always measure first. Premature Flyweight is a common mistake. To recap, Flyweight is about separating the state that never changes intrinsic from the state that depends on context extrinsic. A factory caches the shared objects, so you never create more than one per unique intrinsic combination. This can cut memory use by orders of magnitude in scenarios like text rendering or particle systems. But it adds real complexity, so let your profiler tell you when the trade-off is worthwhile.